Our understanding of the universe is a tapestry woven from observations, theories, and a good dose of wonder. For decades, the Big Bang theory has reigned supreme, describing a universe born from a single point of unimaginable density and temperature. But what if the universe had no beginning? What if it has always existed, constantly evolving, yet eternally present? This is the premise of the steady-state universe theory, a captivating alternative that challenges our cosmic perspective. Imagine a universe not as a finite entity with a defined starting point, but as an infinite expanse stretching through time and space. In this model, the universe is not expanding from a single point, but rather maintaining a constant average density. While galaxies move apart, new matter is continuously created to fill the gaps, ensuring a universe that looks statistically similar throughout time. This theory, while seemingly radical, has its roots in the elegance of a universe without a beginning or an end. It resonates with the philosophical idea of an eternal cosmos, constantly renewing itself. But how does this model account for the observed expansion of the universe and the existence of the cosmic microwave background radiation, considered remnants of the Big Bang? The steady-state universe theory proposes intriguing explanations for these phenomena, relying on the fundamental forces of the universe and the potential for new physics beyond our current understanding. In the following sections, we will delve into the intricacies of this theory, exploring its unique perspective on gravity, matter creation, and even the role of humanity in the grand cosmic scheme. One of the cornerstones of the Big Bang theory is the cosmic microwave background, CMB radiation, a faint afterglow believed to be a relic from the universe's hot, dense beginnings. But how does the steady-state model, without a singular explosive event, account for this pervasive cosmic echo? And the answer, proponents argue, lies in the intricate interplay of gravity and electromagnetism. Imagine a universe permeated by a static gravitational field, an invisible web of attraction holding everything together. This field, while constant on a large scale, experiences fluctuations due to the movement and distribution of matter. These fluctuations, though minute, can have profound effects. These gravitational ripples interact with electromagnetic fields, the fundamental force governing light and other forms of radiation. This interaction, according to the steady-state theory, generates photons, the elementary particles of light, effectively birthing the CMB radiation we observe today. This explanation diverges from the Big Bang's view of the CMB as a fading afterglow. Instead, the steady-state universe proposes a continuous process where gravity, through its subtle dance with electromagnetism, constantly replenishes the CMB, ensuring its presence throughout the universe's eternal existence. This intriguing concept highlights the elegance with which the steady-state model attempts to explain observed phenomena through known physical laws. The birth of galaxies, those majestic islands of stars, gas and dust, is another cosmic phenomenon explained differently by the steady-state model. While the Big Bang posits that galaxies formed from the primordial soup shortly after the initial expansion, the steady-state universe offers a more localized and continuous process. Central to this model is the concept of localized Big Bang events. These aren't Big Bangs in the traditional sense of a universal origin, but rather smaller-scale events where matter spontaneously comes into existence, triggering the formation of new galaxies. These events, scattered throughout space and time, ensure a continuous supply of fresh matter, counteracting the dilution effect of the universe's expansion. Imagine these localized Big Bangs as seeds sprinkled across the cosmic canvas. Each seed, a pocket of newly created matter, becomes a gravitational nucleus, drawing in surrounding material and eventually igniting into a brilliant galaxy. This process, unlike the Big Bang's single epoch of galaxy formation, occurs perpetually, ensuring a universe teeming with galaxies of all ages and stages of development. This continuous creation of matter, while a radical concept, elegantly addresses a key challenge faced by the steady-state model, maintaining a constant density universe despite expansion. These localized Big Bangs act as cosmic fountains, replenishing the universe with fresh material, ensuring its eternal and unchanging character. One of the most enduring mysteries in cosmology is the dominance of matter over antimatter in the observable universe. According to our current understanding of particle physics, the Big Bang should have produced equal amounts of matter and antimatter. However, our universe seems to be overwhelmingly composed of matter. Where did all the antimatter go? The steady-state universe offers a different perspective on this puzzle. Instead of assuming a single event that created all matter and antimatter, the steady-state model proposes a continuous creation process. In this model, matter and antimatter are not created in equal amounts at every location, but rather with slight fluctuations. Imagine regions of space where matter creation slightly dominates, and other regions where antimatter has a slight edge. These fluctuations, though small, could lead to the overall dominance of matter over time. As matter and antimatter annihilate upon contact, releasing energy, these fluctuations could result in a universe where pockets of matter persist while antimatter is largely eradicated. This explanation remains speculative, as the exact mechanisms of matter creation in the steady-state model are still under investigation. However, it highlights the theory's ability to offer alternative solutions to long-standing cosmological puzzles. Instead of relying on conditions in the very early universe, the steady-state model seeks answers in the continuous interplay of fundamental forces and the possibility of new physics yet to be discovered.